This is our large two-sample z-test for percentages. Just like we had a two-sample z-test if we wanted to compare two population averages, we'll do the exact same thing with a two-sample z-test for percentages. It's going to look almost exactly the same. The only difference is the formula we use for our standard error. So we use this test if we want to compare two population percentages. And we have to have independent samples, or we can compare two randomized groups to see if a treatment's effective. The way it works if you compare two randomized groups is you have a little bit of bias in one direction because they're not independent samples, but then you have a little bit of bias back in the other direction, so it kind of cancels out and it works. So theoretically, you have to have two independent samples or compare two randomized groups. And you have to have both sample sizes to be large. So for our preliminary work, you have to find the standard error for the percentage for both samples separately, just like we did for our two-sample z-test for averages. So standard error for percentage is supposed to be population percent times 100% minus the population percent over the sample size. Now in this case, we don't know our population percentage, and when we did it for one sample, we said, well, we think our population percentage is supposed to be like, say, 40%, and we could use that. But when we compare two population percentages, we don't even do that. We don't have some proposed null hypothesis value of what we think the population percent should be. We're only actually comparing two different ones. So we have no idea what the population percentage is. So what we'll do is we will estimate it. I'll do these little wiggles for estimate with the very best estimate we can. If we don't know the population percentage, we don't have a guess for the population percentage. The only thing left to us is our sample percentage. So we'll use our sample percentage here. So it'll be sample percentage times 100% minus the sample percentage over the sample size. Now, you don't need to memorize that this is a second formula. It's just when you go through your work, you'll realize, oh, I don't have any other percentages to plug in, so you plug in what you have. Then you find everything for the difference. For all of our tests, we've had to do an observed, an expected value, and a standard error. So observed difference, well, that will just be, well, what sample percentage did you get first minus the second sample percentage? Now, expected value for the difference, if your population percentages are equal, you'd expect the sample percentages to be about the same, right? So you'd expect the difference to be 0. And the standard error for your difference, just like with averages, it'll be the square root, and you'll do the first standard error squared plus the second standard error squared. Our test statistic, z equals observed minus expected value over standard error. And we just put differences there to remind ourselves we're doing differences, and mostly to remind ourselves to use this standard error for your difference formula. And once again, the p-value will just be the area in the tail, or maybe tails, under the standard normal z-curve. So if you think the population percentage for A is less than the percentage for B, you'll find the area to the left. If you think the population percentage for your first one is greater than the second population percentage, find the area to the right. And if you think it's different than, you'll have to find the area in both tails. So if you think it's different, find the area in both tails. Now again, this only works if you write everything in the same order with like A first, or whatever. That means whatever you put first in any of your calculations, you keep in the same order the rest of the time, and then this little trick will work. So our remarks, I think we've already said them all, but let's just go through again. So again, we don't know our population percentage, and we don't have a proposed population percent because we're comparing two different populations. So we have to estimate our population percentage for the standard error with our sample percentage. And if your population percentages are equal, you'd expect the sample percentages to be about the same. So you'd expect that difference to be 0. And determining if a sample size is large enough is more complicated for percentages than it is for averages. So just assume that every problem I ask you to do for percentages is large enough. I'm not going to make you check. So example, do people see billboards? A billboard company takes a simple random sample of 500 Salt Lake City residents, and they find that only 26 know that Calvin Coolidge was the 30th president. They then put up several yellow billboards that say Calvin Coolidge was the 30th president. After a few weeks, they take another separate independent sample. Remember, independent samples means the two samples didn't affect each other in any way. And 158 answer correctly. Is this evidence that people in Salt Lake see the billboards? So let's write our information that they gave us. We kind of have a before group and an after. So before, we had a sample size of, let's see, 500. And 26 could answer correctly. So my sample percentage equals 26 divided by 500. But you have to times it by 100% to get back to a percent. So 26 divided by 500 times 100 gives me 5.2%. And for my after information, let's see, we have again a sample size of 500. And my sample percentage equals 158. There were 158 of them out of 500. And don't forget to times it by 100% to make it an actual percentage and not just a decimal. So 158 divided by 500 times 100 equals 31.6%. Now, I haven't done the rest of the problem, but we went from 5% they could answer to 31% they can answer. To me, that seems like it's probably going to be a big difference. But humans are known to be wrong when we just rely on our judgment. That's not mathematical. So let's go through the actual math of it. Now, I haven't done my hypotheses yet, but just since I'm here writing the information, I might find the standard error for the percent for both of them, just while I'm thinking about my numbers. So standard error is always supposed to be equal to your population percent times 100% minus population percent. Now, I'm writing this because this is the formula I've memorized, and I don't want to have to memorize another one. So population percent times 100% minus population percent all over sample size and take the square root of everything. Now, we don't know a population percent. No one told me what my population percent should be. So what percentage am I going to use? The only percentage I know about anything for this is this 5.2. So let's use that. So we'll do 5.2% times 100 minus 5.2 all over my sample size of 500, which should give me 0.99% as my standard error. Let's find the standard error for my percentage for afterwards. So again, we're just kind of estimating it with that sample percent, so I'll do the little wavy signs, because that sample percent is the only thing I know about the after group. So we'll use it. So 31.6 times 100 minus 31.6 all over my sample size of 500 gives me 2.08%. So that's my standard error for after. Now we'll write our null and alternative. So I know I keep saying I like to write my alternative first, but I don't often do it just because the null is written first. Let's write the alternative first today. So we want to see, what are we asking? Is this evidence that people in Salt Lake see the billboards? Okay, let's see. If they see the billboards, there should be a higher percentage that answer correctly. So I wrote before first up here, so I want to make sure I keep before. So before percent should be what compared to the after percent. So if people in Salt Lake see the billboards, the percentage afterwards should be bigger. But I wrote before first, so I'm going to write the smaller percent, the before percent should be smaller than the after percentage. So let's see, we could say something like the percentage of all people in Salt Lake, since this is where I was, the percentage of all people in Salt Lake who could answer before the billboard is less or smaller than the percentage that could answer after the billboard. And as far as your boss, she could be like, the alternative then is that the billboards made a difference because the percentage changed. For your null hypothesis, then, that would be just the status quo, that they're the same, there's no difference. So the percentage of all people in Salt Lake who could answer before the billboard is the same as the percentage that could answer after the billboard. Observed percentage, sorry, this is why we write the little things to keep track. I'm going to come off here to remind myself what I'm trying to do. Z, we're trying to deal with differences, so it's going to be the observed difference minus the expected value for the difference all over standard error for the difference, because we're dealing with differences. So now I need to make sure I write observed difference. That will remind me what I'm doing. So observed difference, well, you just take the difference in your two sample percentages. What are your two sample percentages? We had 5.2 and 31.6. So again, make sure you just write that 5.2 first. So 5.2 minus 31.6 gives me negative 26.4. That was my observed difference. My expected value for the difference, well, you're always assuming your population percentages are the same, so your sample percentages should be the same, about the same. So your expected value for the difference is 0, give or take some chance error. And standard error for the difference. This is why it's important to label as difference, because I think, oh wait, standard error for difference, I know that formula. That's equal to the square root of standard error, your first standard error squared, plus your second standard error squared. So our first one is 0.99, so we'll square that, plus the second one, which was 2.08, and we'll square that. So it gives me, the standard error for my difference is 2.3. Now that I've done all the preliminary work, I can come over to my test statistic of Z. It's equal to my observed difference, so negative 26.4, minus my expected value of my difference of 0, over standard error of my difference, which is 2.3. This gives me negative 11.5 as a p-value. Now, in case you're wondering, that is a gigantic z-value. That means I'm 11 standard errors away. This is so far off the charts that it is going to be an incredibly small p-value. So my p-value, because we did less up here, I'm going to look for the area in the left tail. And it's going to be really, really far off the charts. So negative 11.5. So if I pull up my charts, remember Z only goes to negative 4 and your area is already almost at 0. So by the time we get to negative 11, my p-value is going to be about 0%. Just for fun, I put this into my computer to see what the true p-value would be, and it is 0.00. That's 0.28066%. As you can see, that is an incredibly very, very small p-value. So basically, we would have, if I wanted to interpret my p-value, so we have a 0% chance, or almost 0% chance, because it is still a chance. It's kind of like trying to win the lottery or something. We have an almost 0% chance of getting such a big difference in our two sample percentages if the population percentages are the same. Or in our specific situation, if the billboard really didn't do anything, we'd have an almost 0% chance of seeing such a big difference in those two sample percentages of before and after. So I'm going to guess here that my null hypothesis is not plausible. I'm going to say this is a small p-value at any level of significance. So I will reject the null hypothesis. My results are statistically significant. That's always say anytime we have a small p-value. And I would say that we have not just strong evidence or very strong, we have incredibly strong evidence, but we have evidence that, and now you just repeat the alternative hypothesis. So the percentage of all people in Salt Lake who could answer the question was higher after they saw the billboard. So the billboard worked and people do see them. At least some amount of people see them. Okay, next example. In the Salk vaccine field trial, which is mentioned multiple times in our textbook, there were 400,000 children that were part of a randomized controlled double-blind experiment. Half of them were assigned at random to the vaccine group and the other half to the placebo. In the vaccine group, there were 57 cases of polio compared to 142 in the placebo group. Is this difference due to chance? A few things here. Notice these aren't ones where we have independent samples, but it is part of a randomized controlled experiment, so we can still use these formulas and our formulas will still work. Let's write down our information in a nice little chart. Let's see, the first thing it tells me is vaccine, so I'll write vaccine. And over here I'll do the control or the placebo. Okay, for my vaccine, I had a sample size equals, it says half of it, so 200,000. That's a pretty big sample size. And my sample percent was what, let's see, half of them in the vaccine group, there were 57. So it's going to be 57 divided by 200,000. This is going to be very small. When I deal with really small numbers, I'm going to use more decimal places. So I think I'll do 4 decimal places on this problem. Otherwise, your answers change a lot. So it's point, let's see, oh, I almost forgot. Make sure you have times by 100. So 57 over 200,000 times 100 should give me 0.0285%. So that's a very small percent. Again, we're going to do more decimal places just because our numbers are so small. For my placebo, we again have a sample size of 200,000. Hardest problem is making sure you type in enough zeros, or the right number of zeros. And your sample percent is, let's see, in the placebo group we have 142. So 142 divided by 200,000 times 100%, which should give me 0.0710%. Now, while we're doing our calculations, let's go ahead and find the standard error for each one, because I know I'll have to do that. So square root, remember, it's supposed to be population percent times 100% minus the population percent over sample size. And you take the square root of all of that. Well, in our case, we don't know the population percent. No one said we think maybe it should be 30% or, well, sorry, in this case, like 0.03% or something. All we know, because we're comparing two populations, is this is our best guess, the sample percent. So we use that. So it's going to be 0.0285%. 0.0285 times 100 minus 0.0285 over a sample size of 200,000. And then you take the square root of all of that, which would give me 0.0038%. So we found the standard error. And for our placebo, let's do that same thing. So square root, we'll do our sample percent because that's all that I know. It's my best estimate of the population percent. So 0.071 times 100 minus 0.071 all over 200,000 gives me 0.006%. Now it's time to write my hypotheses. Let's first figure out what we did here. It says, is the difference due to chance? Now, I would assume that I would probably be hoping that the vaccine group is better. So I'm going to actually change this problem statement. It'll be changed by the time you get your notes. And I would say we want to ask, does the vaccine help? So in that case, we would say, let's see what. We would want the population percent for vaccine to be what compared to the population percent for the placebo. Well, if the vaccine helps, there should be less people that get polio in the vaccine group. So this should be less. That's what we want to show. So we'd say something like the null would be that the population percent that get is less for the vaccine group than the placebo group. Oh, sorry. Null hypothesis is that they are the same. Null is always the same. The alternative is what you're wanting to show. So the null would be that the vaccine and placebo are the same. They don't make a difference. Vaccine doesn't work. The alternative, though, is what you want to show. Would be that the population percent that get polio is less for the vaccine group than it is for the placebo group. Which means what we truly care about is that the vaccine works. The next step after your hypotheses is then you want to find your test statistic. And we could start writing our formula for our test statistic, which is z equals our observed. Now we're dealing with we're comparing two things, so we'll look at the difference, minus the expected value of the difference, over standard error of the difference. But when I start writing that down, I'm like, oh wait, I haven't actually found any of those things yet. So it kind of cues you in that those are the three things I need to find if you can't remember what you have to find. Because this z equals observed minus expected over standard error, that will be on your formula sheet. But all the rest of it's not necessarily on your formula sheet. So this helps you remember what you have to find. So observed difference, well, that's just what were your sample percentages and subtract them. So 0.0285 minus my other percentage of 0.0710 gives me 0.0006%. negative 0.0425. My expected value of the differences, well, again, your null is always that your two population percentages are the same, so your sample percentages should be the same, so the expected value of the difference should be 0. And standard error for the difference. Make sure you use the one for the difference, because that is going to be your first standard error squared plus your second standard error squared. The reason we do this is it kind of pools and combines our two different standard errors, so it kind of gives us like some, not really an average, but some way to compare the two standard errors, that they're both accounted for. So it'll be 0.0038 squared plus 0.006 squared, and take the square root of all of it, is 0.0071. Now that we have everything, we can plug it into our test statistic. So our observed is negative 0.0425 minus 0 for our expected over 0.0071. This is going to be 5.985. That's my test statistic. So we were almost 6 standard errors away. That's going to be pretty surprising. We should be getting a small p-value. Oh, excuse me. This was a negative 0.425. I forgot to put that in my calculator. So it should be negative 5.98 for my test statistic. For my p-value, because we said it should be a less than, we're looking in our left tail. I have way out here in the tail, z equals negative 5.98 is going to be way off in the tail. When I go to my normal table, negative 4.0 is as far as I go, so negative 5.98 is going to be way up here, and that area is going to be about 0. So it's going to be almost 0%. So my p-value is almost 0%. What would that be if I tried to interpret it? Well, the interpretation is always, that's our chance of getting our sample data or something more extreme if the null is true. So that would be, there is a 0% chance, or almost 0% chance, of getting our sample data. So getting such a big difference in the percentages if there is no difference between the vaccine and the placebo. Looking at this, this is, of course, a small p-value. No matter what you compare it to, it's going to be a small p-value. And so I will reject the null. I could say that my results are statistically significant. And my conclusion would be that we have evidence that the population percent that gets polio is less than the population percent, that gets polio with the vaccine is less than the population percent that gets polio with the placebo. Let's go to the summary of our Z and T tests. So every Z and T test for percentages and averages has this formula. Z equals R observed minus expected value over standard error. So we've gone through like a 1 sample Z test, we've gone through 2 sample Z tests, and we've done that for averages and percentages. We've also done a T test. Now I say every test has that formula, and it's either Z equals observed minus expected over standard error, or for our 1 T sample test, it's going to be observed minus expected value over standard error. Now for this class, the person in charge, they do a very small formula sheet. So this one's not going to be on there because it's exactly the same as this. And you just have to kind of remember to put a T instead. What you have to remember is the formulas for expected value and standard error, which again are all very, very similar, just with slight tweaks. So large sample z-test for average, well, your expected value for your average would just be equal to your population average. And standard error for your average is SC over square sample size. So this formula would be on the test, and this formula would be on the test. But expected value for your average, she's going to assume that you can just remember that. Okay, small sample t-test for averages. Well, it'll be the same thing. We just have that z test statistic up here. But you'll do expected value of average is equal to population average. If the null is true, these are all basically if. Every single one says if the null is true. It's not written down, but that's implied. But your small sample t-test for averages, you have to remember to correct. You'll have to do the SD plus is equal to square root of number of measurements over number of measurements minus 1 times SD. This one will be on your formula sheet. Standard error for average is the same thing, but we do remember to use that SD plus, but we're not going to write this formula on there again. You can just kind of remember from SE average. And your degrees of freedom equals sample size minus 1. I'll put that on for this exam, even though she doesn't, but for the final, you might have to memorize it by the time you get to the final. Small or large sample z-test for percentages would be your expected value for percent equals your population percentage, if the null is true. And the standard error, again, is this nice long formula. Well, your two sample z-tests for averages and percentages, oh, sorry, I didn't say, this formula will, of course, be on your formula sheet as well. If you wanted two sample tests, we actually use the same formula for averages and percentages, so it makes it easier. Your expected value for your difference will always just be equal to 0. And the standard error for your differences is the square root, and you do the first standard error squared plus second standard error squared. So again, just to point out, they all use the same basic formula. Okay, so that's the formula you memorize, and then you just have to remember, oh, how do I find the standard error for the different things? There's a standard error for averages, but there's a different standard error for percentages.